Okay. Okay, so we're talking about ways to bang on the duality and get new interesting dualities. And as I was writing this lecture, I realized there was a lot of material, and you all have been such a feisty audience that I could imagine we could get stuck for most of the period on any item on the list. And so I was actually going to write a time cutoff on each subject, but I'll simply every once in a while look at the list and get nervous and cut off questions probably. Anyway, actually the first two are probably the longest single items. So last time we talked about staying within a given, the n equals 4 theory, say, and just looking at non-conformal vacua of the Coulomb branch. The next simplest thing would be to perturb the theory a little bit to add some relevant operator to the Hamiltonian density of the CFT. And I'll suppose here this is again relevant, delta less than D. If it's irrelevant, it does nothing at low energy. It blows up in the UV and you don't really have a theory anymore in general. Actually, the case delta equals D is interesting, but there's only so much time, so I'll just put a few references in the notes. Anyway, with delta less than D, this is something which becomes effectively larger as you flow to lower energies, and so it should change the low energy physics. And we know how to study this in the dual theory, in the gravity theory, because this is adding this to the Hamiltonian is just what we've been doing to make a generating functional. And we've been thinking the generating functional as just being a way to generate the correlators of the original theory, but it's equally well a quantum field theory in its own right. So with the sign conventions I was using, this is taking that J of x I was coupling to the operator and just setting it to some finite constant value. I think actually there's a sign convention, yeah. So we now have some perturbation of the boundary conditions. And remember, this means turning on a non-zero value for the previously fixed mode. So the bulk field goes as z to the d minus delta, which is just right. When delta is less than d, this grows as we move away from the boundary towards lower energy, exactly like, of course, the corresponding operator. And then we have to figure out what happens when the perturbation becomes large at large z, low energy. Things become nonlinear, and then we have to figure out what happens next. And there's actually, within the n equals 4 theory, there's a nice example that, a rich example that I'll describe, which is to add to the superpotential masses for 1, 2, or 3 of those n equals 1 superfields. So 1, 2, or 3 non-zero. And this is going to have to be fairly descriptive, and this section of the written notes will be heavy on references. This is more a guide to what people have done than a lot of details. But I'll tell you what, for one non-zero mass, it's believed to flow to a new fixed point. A new strongly interacting fixed point. For two masses, it's believed to flow. For two masses, what's left, the massless part, is just the n equals 2 gauge theory, which is just the subject of Seiberg-Witten. It's believed to flow to an SUN version of Seiberg-Witten. Which in particular means that the massless sector is a U1 is non-interacting. The massless sector is a just a U1 subgroup of the original non-abelian symmetry, which means in particular it's non-interacting. With three masses, the massless sector, the chiral superfields are all massed out. What's left is the n equals 1 gauge field, and that's believed to be a confining theory. And so with 3 masses, it should confine. That's expectations from various kinds of field theory reasoning. And it's interesting to see the way the geometry reflects all of these. Tom?
Yeah, you could also plug with 2 masses to an Argyros-Douglas moment or something along that.
Well, that's a special point within that space.
It doesn't go to U1 to the N-1.
Oh, I'm sorry, you're right. I'm sorry. Actually, I had forgotten it. Let me come back to that, because that's a really good point. Good. So let's see the way that the geometry reflects all of these. So now I mentioned for a while back what the dictionary was for these operators. They correspond to this 3-form fluxes on the 5-sphere, and the 5-sphere has no 3 cycles, so these are not typological. They're not monopoles. They're some kind of dipole 3-form fluxes. And the supergravity folks have a trick for studying these called consistent truncation, where they write down an effective 5-dimensional theory with this mode and then solve it. And it's really magic because there is no symmetry that would prevent this. The particular mode here, it's some harmonic on the sphere. It's not lower in energy than the other harmonics by a lot. Symmetry doesn't keep from mixing with them, but there's some supergravity magic where they can write down a 5-dimensional Lagrangian, solve it, and then lift it to a 10-dimensional solution, and it can be applied to this case. And so first, for the case of one massive flavor, when they do this, they get a 5-dimensional potential that looks like something like this, where the n equals 5. So this is a potential for this mode. The n equals 4 theory that we've been dealing with lives up here, which seems kind of unnerving. But as we discussed, this mode has a negative mass squared, but if it's not too negative, then the boundary conditions stabilize the system a la Brighton, Lohner, and Friedman. And it's okay. That's the situation. In fact, we know we're in this situation because if you go back to the the m squared equals delta minus d dictionary, being relevant, that is delta less than d, exactly means being tachyonic in the supergravity, and you can kind of guess what happens. There's some solution where the field rolls. So here's its value at the boundary. Here's its value at the horizon. And there's some solution which has, here's z equals 0. Here's z equals infinity. Here's an ADS region. There's some transition region as you roll down the potential. And then there's a new ADS solution. So this is this is a particular this is exactly what the field theory reasoning leads one to believe, that you flow from one strong coupling theory to a new strong coupling theory. You can match up the details of what you expect. Yes.
Did you say the unstability at G equals 0?
I'm sorry.
Unstability at G equals 0.
This instability?
Yeah, that corresponds to the BF bound.
The BF bound is satisfied here, meaning that there is no instability. And Tom talked about this too. There is no instability in time, but there's in some sense it's not really an instability. But you don't roll down this thing in time because the gradient energy protects you. But you can roll down it when you travel in a space in the radial direction, and that's what you're doing.
I don't quite understand what instability.
Sorry?
I don't quite understand what kind of instability you say.
I mean, I'm sorry. I'm just instability. If you see a potential like this, you don't expect this to be stable. This solution. That's all I'm saying. And I'm saying that it is stable because I'm not sure. Maybe I'm understanding the question, but I'm saying the system is stable because there's also gradient. There's also gradient energy that if you look at time evolution, actually, turns the potential up.
I'm saying that in the dual gravity theory, what kind of instability do you have situations?
In dual gravity theory, you have this is the potential in the gravity theory. Sorry, this is the potential in the gravity theory. And when you look at the radial equations, there are solutions which start here and end up here. Now, with two masses, you can do the same thing, and there's some other direction in the potential that you're flowing in, and this one's different because you end up flowing sort of out to infinity in field space. With two masses, this same strategy, when you lift it to a 10-dimensional solution, gives you a singular solution. So this is with one mass. It does what you expect. Two masses gives you a singular 10D solution. But it's actually not a bad singularity, because then you look at it carefully and you realize that it's just a bunch of D3 branes. And so what the geometry is here is that, well, let me draw ADS space, Poincare ADS space. This way, this is z equals 0, the boundary, and the spatial things are shrinking off. And it never gets to z equals 0. It kind of, it's a bad way to draw the picture. But the point is that the whole space, gee, no, I should really be drawing I didn't think in advance. The point is that you never get to z equals infinity. The geometry smoothly rounds off. This is actually not the ADS, but the compact directions here. And this is z equals 0, and they smoothly round off at some z equals z max. In terms of the metric, you have this ds squared is L squared over z squared, eta mu dx mu dx nu. And again, in the ADS geometry, one has arbitrary low energy excitations by moving an excitation to smaller and smaller z. That reduces its energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that. And so you have a mass gap. So whenever you turn on a relevant perturbation to a conformal theory, there's a good chance that all you're going to do is give mass to everything. And on the geometric side, that's reflected by capping off the geometry. Here, though, it works out that you've got this plus you have n minus 1 d3 branes. No, n d3 branes, sorry. There's the minus 1 is a distraction we won't talk about. The n d3 branes. And so the bulk theory exhibits exactly the massless sector that you would expect from the field theory. And the thing about Seiberg-Witten is a whole moduli space. These D3 branes actually have lots of places that they can sit. And it's true that when you bring them together in certain ways, you do get, as Tom reminded me, interacting fixed points. And actually, you would expect then on the gravity side to get some interesting geometry as you reach those points. And I remember thinking about this years ago and never sorting it. Do you know if anybody ever sorted that out? Homework problem. Pardon? Yeah, it's a great question. I mean, yeah. I mean, so I guess part of the problem is that the supergravity folks first have to tell us what the metric is for arbitrary distributions of D3 branes, because this trick gives you special distributions. If they would tell us what it was for arbitrary distributions, then one could bring it to the RGS and find out what is the geometry.
You also, in order to get a nice geometry picture of this new fixed point, it has to be something special that happens in SUN for large n. And we don't really understand
Okay. Right. You're right. You say we understand it for small number where it might not be in the geometric regime. Good. Okay, and with three masses, you try again the same trick. That is, you get some potential, you follow it off. The 5-dimensional solution you get lifts to a singular 10-dimensional solution. Question?
Starting from n equals 4, you just deform by 2 masses, and then you said you take this thing.
Yes.
What decides which point in the modular space is it?
A good question. This consistent truncation magic chooses a particular point in the moduli space. And of course, in fact, of course, when there's a moduli space, I mean, it's the consistent truncation is just a solution generating trick that doesn't capture everything. For a while, it was a goal to try to find the gravitational description of the general point on the moduli space, but it seems to be beyond the supergravity technology. You know they have to be there, but to actually describe them explicitly, the back reaction of the D3 branes explicitly, seems like an open question. The people who've done the most on this are Pilch and Warner, and they pushed on the problem, made some progress, but I don't think they ever gave a general solution. Question?
It's just a question about this consistent relation. So I think the statement is that any 5D solution can be lifted to a, well, I was going to say smooth 10D solution.
It's not smooth when the fields run off to infinity.
Yeah, but is the lifting unique, or can there be multiple?
No, it's unique. That is, as a recipe. They look at the supergravity field equations, and it's a trick, and it's a trick which, and it certainly is 1-to-1 in the way it's used now. Yeah.
It doesn't say that there can be some other solution, not the one you got by this trick, which.
Right. In fact, let me come to an example. In fact, when you get to three masses, this becomes even starker because, let me say what happens with three masses. With three masses, you can do the same thing. The 5-dimensional thing flows off. You get a singular 10-dimensional solution, but it's not any recognizable, sensible brane.
Is the singularity resolved if we lift the solution to Lardy supergravity?
I'm sorry?
Is the singularity resolved if we lift the solution to Lardy supergravity?
No. This is in 2B, so there's no 11D left.
We could serialize along some given direction that will try to.
Yeah, well, again, the two-mass singularity really is just D3 branes. Let me finish this telling you what happens with three masses. So with three masses, if you're Matt Strassler, you look at the gauge theory side of the duality for inspiration. If your superpotential is, W is m alpha, then all the masses equal, say, phi alpha squared plus epsilon alpha beta gamma, commutator of phi alpha with phi beta, phi gamma. This is all traced. And I'm leaving off the constants. Then the F-term equations tell you that, again, I'm leaving off the constants. M phi alpha is epsilon alpha beta gamma, commutator of phi beta with phi gamma, which is to say that you have vacua for any. So again, these are n by n matrices, and you have vacua for. So there is one vacuum for each n-dimensional representation of SU2. That is, it doesn't have to be reducible. So there's a huge number of vacua, including the trivial one, phi equals 0. And phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Higgs-Coulomb behavior. But remember that the scalar parts of these superfields arose as the coordinates of the D3 branes, and this is saying that those coordinates are becoming non-commutative, which comes back to the question from the last lecture, because Rob Myers explained that when you put D3 branes in a transverse flux, it becomes energetically favorable for their coordinates to become non-commuting, and they puff out in two directions to become D5s. And so the correct behavior of the supergravity with three masses is that it ends on It can actually end on a D5 or an S5, or in fact sums many 5 branes. And the fact that there are many ways to cap off the geometry reflects the fact that that the theory has many vacua. And so there's a nice match between, you learn from this several things, of course. There's a nice match between field theory expectation and what supergravity tells you, but also it takes some trial and error in many cases to figure out where the geometry flows to. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry then does. And in particular, it's useful to have insight from the gauge theory as well. By the way, you can once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brane. It was smearing the 5-dimensional object out into like a 6 or 7-dimensional object. And so it was trying very hard to give the right answer. Okay. Now, the last thing I want to say about, I'm pretty much on schedule. The last thing I want to say about this is, I told you that one of these theories confines, and I want to tell you how to see that. So one observable I didn't talk about is to measure the potential between a source, a quark and an anti-quark source, fundamental and anti-fundamental. That maps, so the QQ bar potential. Fundamental. There are fundamental. You can always get fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it in going back to Tufte and Wilson, is thought to be the color electric flux tube. And one could say more to justify this, but time is short. The way you calculate the potential is to consider a string hanging down from the boundary, and then subject to suitable renormalizations, the potential is just the tension of that string. The potential is just the total energy of that string coming from its tension. Now, the tension, the effective tension, so again, this is the z direction, is the local tension times the translation, the gravitational redshift, the other way around, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further in z it hangs. And in fact, in an ADS phase, you get, as you must get, because just by its scale invariant, just matching units, as you pull the ends further apart, the string hangs down lower, and so it can reduce its energy, and in such a way that the potential goes as one of ours. It must by symmetry. The coefficient's interesting, but no time for that. In a confining vacuum, on the other hand, we have encountered this idea that there is some Zmax. And so, let me draw this a bit larger. The string hangs down, but it can only hang down as far as the space lets it. and then you pull the ends further and further apart, and most of the string is just running along the bottom of the space at the largest value of z, the most infrared value of z you can get. And so the effective tau of the string is just, it's non-zero. It confines. And that's what happens with 3 masses. With 2 masses, the Seiberg-Witten vacua are not confining. They're Coulombic, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the 2 masses. But there's also those explicit D3 branes. And so now I'm going to draw the same picture. So here's z equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those D3. So I'm looking now from a perspective that sees the 3 directions more explicitly. And so here's your D3 branes sitting at the bottom of the space, and the strings hang down. But once a string ends on a D3 brane, it doesn't go, its source is flux. But the flux is just a U1 gauge field, and it's free to spread within the D3 brane. And so you get a Coulomb potential for a different reason than you did in the ADS space, but it's still Coulombic. That's a general thing. When D3, when a lower dimensional object dissolves in a higher dimensional or ends on a higher dimensional, it doesn't just end. There's always some, should have the arrows running the other way, I guess. There's always some flux carried by these objects, which has to somehow run through the higher dimensional object. But again, because the 3 branes have abelian gauge fields, the flux can spread freely. Okay, so that's the general idea of RG flows and also some specifics. Yes? Yeah. So, I mean, you've got strings, you have D strings, and you have PQ bound states. So, yeah, you have the entire sort of SL2Z multiplet of charged objects. So, in fact, I mean, with all of these phases, you also want to ask about the 't Hooft loop, the status of the magnetic, potential between magnetic objects. Are they confined? Are they Coulombic? And there's always an analogous story for those. And similarly, you can ask it for external dionic sources. Now, some CFTs have operators in the range between the minimum allowed by sort of unitarity, by the conformal algebra, and half the dimension of the space-time of the CFT. And this is the regime where, as we said, you have to take the alternate boundary condition, the less obvious one, on the scalar field at z equals 0. But this is also special for another reason. It's special because 2 delta is less than z, less than d, and so the double trace operator, squaring the original operator, is relevant. Now, and again, I'm using here large N factorization. In the large N limit, the amplitudes for the two, so you have 2 operators at a point, and they're each connected to the rest of the graph, but the leading in N amplitudes are fully disconnected between the 2 operators, and so its dimension is just twice the original dimension. And so we want to see where this goes, and it's an interesting story. So, for a couple of reasons. So, let's see. Let's perturb. So we have our generating functional for the original CFT, and now we're going to add to it a double trace perturbation. And a nice way to think about this is to introduce an auxiliary field. And so understanding where this theory goes to isn't going to be so hard, because we can just use this trick to rewrite it in terms of the theory we know more about, the theory with just single trace operators turned on. And this is, in fact, just by the usual definition. Now the integral d sigma e to the minus 1 over 4g integral, and then the usual z sub j plus sigma. Just the generating functional for the single trace correlators. Okay, now we can now do the sigma integral in the large N limit. We can now do the sigma integral just by saddle point. We can just find its saddle point. And actually, one can probably do this. Probably even is the right answer beyond large N, but let's keep things simple. So let's let's evaluate this by saddle point, and the saddle point is at 1 over 2g sigma. So the saddle point is at 1 over 2g sigma equals partial z partial sigma, which but this is just the generating functional. So differentiating it once with respect to the source just pulls down the expectation value. And if we go back to our original dictionary, a given operator in the CFT is just the normalizable mode of the quantized mode of the quantum field in the book. And so this is alpha, the quantized mode, as a function of beta equals j plus sigma. The fixed mode is set to these values, and then you evaluate the quantized mode. And if we now plug in, rewrite what we have here is that 1 over 2g. Okay, actually, there's one of my c sub o's here, some constant 1 over 2g beta minus j is equal to c sub o alpha. So what you see is that introducing the double trace perturbation is equivalent to introducing a boundary condition of this form. And there's some constants floating around that aren't so interesting. And forget j for now, which is just, again, a source we're using to build a generating functional. The basic statement is that we now have a generalization of the previous boundary conditions, where instead of one of alpha and beta being set to 0 or to a fixed value, they are proportional to each other with some constant of proportionality. And we can now figure out, so now we can write, let me again, the j is uninteresting. It's just, again, to build a generating functional. So to keep things simple, we now have we can now write the mode expansion at phi is alpha z to the to the d minus delta plus beta z to the delta. We're in the regime where delta is less than d over 2. So this is the larger mode at the boundary. Sorry, wait. No, yeah, that's right. This is the larger mode at the boundary. This is the smaller mode at the boundary. But the point is that since alpha and beta are now both turned on, there's just some constant proportionality between them. So I can make one of these, I can write one of these in terms of the other times a constant. There's just one definite linear combination of these two terms turned on. And the point is now that if you go towards the boundary, this mode dominates, and it looks like the alternate quantization, the one that we started with in the UV to get that range of dimensions. But in the IR, this mode is the one that dominates, and it looks like the usual quantization in which delta, the effective dimension operator, is now changed to d minus delta. So what this is describing is a flow between the two possible boundary conditions for the given bulk mass squared. It's a flow. So what we call the alternate quantization, that is the quantization in which you have an operator whose dimension is in that range. That happens. It doesn't actually happen. There are no such operators in the n equals 4 theory. But in many variants of the n equals 4 theory, you do have operators whose dimensions are in that range. But in fact, as a sort of point of naturalness, that's unnatural, because if you turn on the double trace perturbation with even a small coefficient, the system will flow to the other solution where that operator moves up to larger dimension. And, well, this has some relevance to, I think, to the to the models of Fermi liquids that Hong will be talking about, where you have various flows going on in the theory. This example also exhibits another idea that's worth remembering, which is that if you look at, say, the second line there, the second line. The second line, we've taken the original ADS CFT theory, and we've added a field sigma that couples to an operator from the CFT. This is just an auxiliary field. Its action is just this local sigma squared. But you could imagine generalizing this structure and coupling fields in where instead of sigma squared, you have some typical, Klein-Gordon action or some kind of non-trivial dynamical action, or even you could make fermionic operators and have a Dirac action. And what does this mean? What this means in this case is that your Lagrangian theory has two pieces. It has a strongly coupled piece, and it has another piece which may be weakly coupled or has just some explicit Lagrangian. And the strongly coupled piece has a gravity solution. These two pieces are coupled together through some interaction like that sigma O up there, some bilinear interaction. And so this is kind of semi-holographic, where you have the strongly coupled piece, and you're using gravity to solve the strongly coupled piece, and then you're coupling that solution to an explicit Lagrangian description of the other part of the theory. And again, this semi-holographic idea, it comes up in a lot of different places. There's no reason you can't. Basically, you're adding fields to the boundary theory by hand, and there's no reason you can't do that. It has a definite physical meaning, as I just said. And again, it comes up in these constructions that Hong is going to talk about. Yes?
So looking at your first line, it seems to that if there exists an asymmetry to prevent the existence of the operator O, then you can turn on the double trace perturbation.
Well, Right. So it's in the n equals 4 theory, that's not invariant under the n equals 4 symmetry, so you wouldn't have it. So that of course that theory doesn't have such operators, but right. So in some cases, if you insist that your starting point preserves supersymmetry, then you don't worry about this. But from kind of a condensed matter-y point of view, you have some UV theory, and you get you get your most general Lagrangian consistent with the symmetries, which will usually contain such terms, which means that it's unlikely in this framework to find operators whose dimensions is in the ultimate range.
Yeah, there's another portion of the point. First, it says that if the single trace operator has dimensions smaller than d over 2, but then the double trace operator might develop large anomalous dimension and wouldn't.
Well, that can happen at small. Okay, good. That can happen at small n. So indeed, and of course, in the real world, n is not so large. And so indeed, we're talking here about things that happen within this large n universe that indeed may not have, indeed, may not continue to be true at small n. Yeah. Of course, at small n, the distinction between single trace and multi-trace begins to break down. When you get to n equals 1, there's no distinction at all. When you get to n equals 2, you've got single and double trace, but then triple trace are redundant. So the whole distinction of single trace and multi-trace is sharpest in the 1 over n expansion. Yeah.
Assume the coefficient of O squared here if it's sign.
Well, yeah, I actually assumed that sign to make it's attractive there to make things work out nicely, which is the sign I also got from the references I was following. It'll be in the notes. Siever and Schomer and Berkhus on this. The other sign is left as a homework problem. I'm not sure what happens. Yeah, I mean, look, you can with the other sign you're probably going to want to put an I in somewhere, and you get some complex saddle point. But I'm not sure if there's any significance to that. Yeah. Indeed, actually, but no. In fact, physically, I'm not sure what happens. Actually, it is certainly obviously there's a big so. The sign really is saying that the sign makes a big qualitative difference because and it could and actually it's an interesting question how it changes this. Tom, do you
Yeah, not about this question,
Yeah.
but there's something I think potentially deceptive here. Namely, if you had chosen a more complicated ultra-local action for sigma.
Mm-hmm. Yes.
You would have gotten some complicated power series in O, including
Right.
a lot of non-renormalizable terms.
Right.
Which doesn't look like it makes sense. But this analysis seems to
Well,
suggest that you could make it make sense.
you know, the way I set things up, I never actually had to regulate the theory by putting in, by cutting off the supergravity theory at some scale epsilon. But if I start writing down things that have non-renormalizable bits, I'd probably have to regulate, and then all those non-renormalizable things would probably turn out to be irrelevant. But yeah, okay. Morally, there isn't. You can go down to dimensions where O cubed, O to the fourth, and so on are relevant. Or you can ask another question: what if I had tried to do this trick and I wasn't in this range, so O squared is irrelevant? Okay, then if you do things carefully, you will find that you probably have to put in a cutoff, but you'll find that the infrared obviously is stable, right? Okay, so those are the two biggest subjects and the only ones that really have a lot of equations with them. Tom mentioned orbifolds and covered the main points. I just wanted to make a couple more points. We're going in this direction of small perturbations of the theory now to large ones, but not so large. orbifolding is a fairly, conventional way to bang on a theory. So we have the 6 directions that are transverse to the 3 branes, and if we divide by if we identify under some subgroup of the rotation group, then the origin becomes a singularity, but in a simple way, and the method of images, tell us how everything works. And so on the supergravity side, on the ADS side, you've just taken S5 to S5 mod gamma, and on the CFT, you have some sort of quiver gauge theory. E.g., with ZK, you get, if gamma is ZK, you get, first of all, you get USUN to the K in the gauge group, and then you get various bifundamental matter charged under different factors, and the details of the matter depend on, there's different ways for ZK, that ZK can act on the spatial coordinates and on the fermions, and so you get different kinds of bifundamental matter coupled into this group with n equals 2, n equals 1, and as Tom says, n equals 0 supersymmetry. Tom mentioned that in the n equals 0 case, as far as anyone knows, there are no conformal theories at weak coupling, right? Pardon? You were talking about weak coupling. You were talking about the weak coupling beta functions, right? When I was in your discussion, I thought you were talking about what the beta functions of the theory do, which are the perturbative beta functions. No, not in this. Not in this. There are double trace operators. What happens at weak coupling is there are double trace operators that run. Right. And I actually wanted to provide the strong coupling counterpoint to that. So in the case that, so again, the amount of supersymmetry can be 2, 1, or 0. In the case of no supersymmetry, you always worry about instabilities, and I want to tell you what they are. So in the first place, if some non-supersymmetric rotation, some supersymmetry rotation has a fixed point on the 5 sphere, there's going to be some tachyon, and the theory will instantly be unstable. What happens generally with these localized tachyons is that some kind of hole forms in the space, and it gets bigger and bigger very fast, and your whole space goes away. You have no gravity side, and you also have no gauge theory side. This is the general sickness that non-supersymmetric field theory, the strong coupling, are typically unstable. Even when, in the non-supersymmetric case, even when you have no tachyons, even when there are no fixed points of the non-supersymmetric elements, you have the same process non-perturbatively. It's just Witten's decay to nothing, where this hole appears not due to a tachyon rolling down its potential, but due to some tunneling process where the whole space tunnels from its original shape to this one, develops a hole, and then grows. So an example of the general phenomenon that non-supersymmetric theories are unstable. In this case, if you're willing to deal with metastability, and there's no reason that you shouldn't be, by putting some kind of UV cutoff on this space, you can, in the case that it's a tunneling instability, you can make the theory hang around for a long time and ignore it, talk about the duality. Okay. That's really all I wanted to say about orbifolds. I wanted to sort of give the rest of the story of the non-supersymmetric case. Yes?
About your first 2 points about the orbifold and argufold.
Yes?
Suppose there is this theory A and then an argufold of theory B, and then we do the same argufold on both sides. Would they still float each other?
I want to say yes. The typical thing about orbifolds is that they don't, if you have, in the large n limit, there's an inheritance. And so you basically take, and so in general, in the leading large n limit, anything that happens descends to the orbifolded theory. If you have something that depends on the next order corrections, then not necessarily. Yeah. Also, once you overfold, you have new possibilities because there are operators in the twisted sectors which didn't exist before. But that gives you new possibilities, and it doesn't destroy the original solution you had. So one can build new examples by combining RG flows and orbifolds. For the supersymmetric orbifolds, you have new operators sitting at the fixed points, and some of them are relevant, and you can imagine turning them on, and now you have some singularity. Well, it can be a whole ring of singularities, and the phi sphere can turn into something like S3 cross S2. So you really can start getting into new topologies, and that's what the conifold is. And by carrying this, it often takes some cleverness and some insight about the gauge theory side of the duality to figure out where the flow goes to. There are people who have figured this out. And this is a special case of a much more general thing, which is that the field theory that on the gravity side, you can replace the S5 with any space which is an Einstein space, in which the Ricci tensor is some constant, positive constant times the metric, and you still get a solution to Einstein's equations with just 5-form flux. Actually, once you add in other fluxes like the 3 forms we were talking about before, you have more general shapes. But if you stick to just the ingredients we have in the ADS5 theory, the 5-form flux and the metric, then you can replace with any x with any Einstein space. And if you want supersymmetry, then there's one more condition. It has to be an Einstein-Sasaki space, which means that in addition to being Einstein, it has to be Sasaki. Sorry, math is not my strong point. But anyway, it means something like that. Yes? Good. I actually knew that, but yeah, what Michael said is that right. The full 6-dimensional space, the cone over it, has to be Calabi-Yau, right? Has to be Ricci flat and also Kähler. Yeah. It also means that the space has a circle in it that's fibered in a certain way. Anyway, if I give you such a space, and tell you, and you have to give me the gauge theory, there's no obvious machine to do that. And this, what machine one has is this sort of idea of using the combinations of renormalization group flows, orbifolding, going out on the Coulomb branch. And so there's a fairly large industry of figuring out the dictionary, which is most complete in the toric case, where there's a U1 cube symmetry of the space. But in the more general case, where there is not so much symmetry, there aren't so many tools. Okay. So we're doing pretty well. So the next item on my list was non-conformal branes. So what if we had started the whole story? What if we tried to repeat the whole story, not with a D3 brane, but with a D2 brane? So with the D2 brane, we get the same gauge theory reduced to 2 + 1 dimensions. And in 2 + 1 dimensions, it's no longer conformal. It's now supernormalizable. It's weak at high energy, strong at low energy. And so what we're going to see is that, well, in the D = 3 case, we varied the coupling. And in one regime, we had the gauge description. In the other regime, we had the gravity description. Here, the energy itself varies the coupling for us. At high energy, we have the so this is the gauge theory. This is the z direction, which means that energy runs this way. I really don't like that. I really like energy running the other way, but everybody's starting to use z, so you got to use it anyway. Okay. And so at high energy, you have the gauge theory as the good description. Now, what happens in the bulk on the other side is that you have the D2 brane geometry. And so it's the same kind of story, but again, just with respect to energy, that is the high energy part. So in the gauge theory, at high energy, it's effectively perturbative. As you reduce the energy, it becomes strongly coupled. On the geometric side, you have some range of scales where the geometry is good, and as you go to higher energy, it breaks down the same way the D3 brane theory did. That is, the curvature becomes large compared to the string scale and can no longer be trusted. So when the curvature becomes large in string units, the gauge theory description is the good one. In this case, there's another fun thing that happens, though, because in addition to the curvature, the dilaton, which was constant in the D3 brane solution, the dilaton blows up. Okay? The dilaton blows up as you go to larger Z, which is lower energy still. And again, that's not a surprise. In the D3 gauge theory, again, the coupling is growing at low energy, and that's reflected in the growth of the dilaton. But at some point, the dilaton becomes large, and we can no longer use the 2A string theory to describe things, and we have to lift to M theory, and the D2 geometry eventually goes over to the M2 geometry. And so this provides one Lagrangian description of the M2 branes. In recent years, other ways to flow to the M2 brane have been discovered. But it's just the same gauge theory that we've been talking about, but in one less dimension. In one less dimension, you might think that it confines, because gauge theories in 3 dimensions really want to confine. Because of the supersymmetry, it can't. And instead, as you get to very low energies where the coupling is very strong, it gives you a realization of the dual to the M2 branes. You can repeat this for lower dimensional branes and higher dimensional. As you go to lower dimensions, you get infrared fluctuations and things get more complicated. But I want to say this. I'm glad Tom is here to correct me. But actually, before I get to that, there's one other thing you can do at this level. We could have taken the D3 branes and compactified one spatial direction. Make it periodic. And if you think about that, on the gauge theory side, the low energy physics should be now one less dimension. It should be so this is 4-dimensional. It should be 3-dimensional. So you'd expect on the gauge theory side that if we compactified one spatial direction, we should flow to this story at low energy. And indeed, on the gravity side, because of the way the metric is pinching off at large Z, the direction that you've identified becomes smaller and smaller. You need to T-dual, and so you get to the D2 picture. And so what I've the different dimensions fit together under compactification and T-duality. you can now do this in 2 more dimensions and take the D3s down to D0s. And I think it's fair to say that the Banks et al. Matrix theory in this way is implied by the ADS-CFT duality. Would you agree, Tom? Pardon?
Not really.
Not really. You never agree. Okay, good.
No, I mean, implied would mean that you could derive from this that the large n limit of that theory had the extra Lorentz invariance that we claim is going to appear. That doesn't follow from this analysis.
Yeah, I agree. When one says derive, one makes assumptions. I mean, one assumption is simply that duality commutes with compactification, which is a pretty safe one, but could be some. Right. So fair. And also you could go in the other direction. In the other direction, I think it's harder to argue that ADS-CFT follows from matrix theory because there you're looking at an extremely low energy sector of the D0 brane quantum mechanics, which doesn't capture the supergravity regime. But what's clear is that these two things are cousins of each other. They're not identical. Neither maybe is fully contained within the other, but they're very close cousins of each other. Okay. You can also go up to D4 branes and higher, and I don't want to belabor the point, but you sort of get the same flow in the opposite direction. Just reverse these arrows, and the gauge theory describes, in that case, the infrared physics because it's non-renormalizable. And as you go to higher energies, you flow to the D4 geometry and eventually to the M5 geometry. Anyway. Good. Okay. You're being a very good audience today, or we're actually going to finish. Okay, so turning more to things that might be useful which are interesting in their own right. Oh, I'm sorry. I want to say one more thing about the 2+1 gauge theory, which I like to harp on the fact that ADS-CFT duality gives a non-perturbative definition of quantum gravity. And, if you're a stickler, you might say, well, do we really have a good non-perturbative definition of the D equals 4, N equals 4 theory of strong coupling? You can put it on a lattice, but it's strongly coupled, and you don't have good control of the continuum limit. So in fact, when I make that statement, I always have in the back of my mind the D equals 3 gauge theory, which is super-normalizable, which means that you can put it on a lattice, preserving gauge invariance, you always want to do that, but without regard for supersymmetry. And because it's renormalizable, you can really analytically control how the supersymmetry returns in the continuum limit because everything's getting weak and you have analytic control of that limit. So that's another reason I like to trot out the D2 brane version of the duality. Okay, now D2s and D6s. So you can start adding more branes in different directions. And again, I'm focusing here on some that are kind of interesting, maybe for the condensed matter connection. So there's a lot of conformal field theories, even non-supersymmetric conformal field theories in 2+1 dimensions. Suppose you have basically that's because to one loop. I want to write the RG equation not for the gauge coupling itself, but for the effective dimensionless coupling, which is that divided by the scale. Let me call this gamma. And then you have mu partial mu gamma squared is minus gamma squared plus b naught gamma to the fourth. And so this is just dimensionful. This is just saying as you go to high. This is just saying this is now again in 2+1 dimensions. D equals 3. As you go to higher dimensions, gauge couplings get stronger. as you go to lower dimensions, higher energy they get weaker, lower energy they get stronger. And now you have a one-loop term. And I want to just play the game of pretending that the one-loop term is the only one that matters. And so if B naught is positive, there's a 0 at finite gamma. And in fact, as you go to lower energies, gamma stops getting strong and slows to a non-trivial IR fixed point. In many cases, I'm not sure how universal it is, actually you can think of B naught as being the same beta function that you would have had for this matter content in D equals 4. And so in particular, we're talking about positive B naught. And so if you have a gauge theory which is infrared free in D equals 4 and reduced to D equals 3, then you get this non-trivial IR fixed point where the dimensional growth of the coupling is balanced by the quantum suppression of it, the quantum screening of it. Actually, there are cases where everything I just told you is reliable. If you have some gauge theory, if you take a large number of matter fields. This is vector large n, just n copies. Then we know that the one-loop beta function becomes more and more dominant. In the large NF limit, the one-loop term is all that survives, and this argument is reliable and gives you weakly coupled fixed points. What happens as you reduce n sub f and you get potentially stronger more strongly coupled fixed points is less clear and depends on a case-by-case basis. But now we can make a dual version of this story by taking D2 branes lying within so these are D2 branes lying within D6 branes. So if the intersection is two-dimensional, and now you have the D2 brane gauge theory, which is this highly supersymmetric thing, and you have additional matter from the 2-6 strings. And the D2 brane theory by itself gives a total contribution of 0 to this, because its beta function is 0 due to the high degree of supersymmetry, and then the D6 branes make a positive contribution. And so when the number of 6 branes is much greater than the number of 2 branes, you have a weakly coupled fixed point. In this case, there's enough supersymmetry to guarantee that this survives as you take more 2 branes or less 6 branes and reverse the inequality. And also in this case, you can actually write down the metric of the dual theory. Normally when you have branes of different dimensions that are localized within each other or when they're fully localized and not smeared, you can't. But here you can secretly use the fact that when you lift a D6 brane to M theory, it becomes an orbifold fixed point. And this is actually just some orbifold version, orbifold of the M2 brane metric, which was given in an earlier homework problem. And again, this is a nice starting point for discussing various phase transitions in these two-dimensional gauge theories. And by the way, there's a regime where this looks like a 2A solution, and there's a regime where it looks like an M theory solution. And it's very similar actually to the ABJM story. It's much older than the ABJM story, but it's similar to that aspect of the ABJM story for a different orbifold of the M2 brane. Now, one reason I'm talking about this is because I told you that I want to make a Fermi liquid. And so the next natural step would be to turn on a chemical potential and make a density of these 2,6 strings. But in this case, because of the supersymmetry, there's both bosons and fermions there. And when you turn on chemical potential, you generally expect that most of the charge will go into bosons because the exclusion principle lets them all get into their lowest energy state. And so you only get a few fermions. And so I didn't think I was going to get to this last item. The last thing I'll probably talk about today is simply to replace the D2 brane with a D8 brane. Where this part of the story still goes through, and this part of the story still goes through. But you're less sure about what happens at strong coupling because now there's no supersymmetry. Actually, the no supersymmetry is good for one reason. Where the strings have codimension 6, the branes have codimension 6, the strings that stretch between them are all fermionic. And this would seem to be a nice starting point for building a Fermi liquid. You take this brane configuration, take its gravity dual, turn on a chemical potential, and let the gravity tell you what happens when you have a density of fermions in 2 + 1 dimensions coupled to a strong, in this case, non-abelian gauge field. It's a question one would like very much to know the answer to. So far, there's a number of problems which keep one from this is the best so far top-down construction of Fermi liquids, and I'm talking about it because I don't think any of the later speakers will, since it hasn't been especially successful so far. There are lots of instabilities. The D2 branes can repel each other along the Coulomb branch. The D2 branes can repel the D8, which actually has a nice interpretation. That's chiral symmetry breaking. It just means that some fermion bilinear has gotten an expectation value. Also, the spherical space, the 6 sphere that surrounds the D2 branes can have modes that are actually BF tachyons. Because there's no supersymmetry, what one in many cases finds is that shape modes of the 6 sphere are unstable, and it just runs off to something you don't know where. That's really annoying because the shape modes of the 6 sphere correspond to scalar operators, as we've seen. And you don't care about the scalars at all. They're artifacts that come along with duality and aren't in the system that you care about. And so it's just one of the annoyances of trying to make a top-down construction. Presumably it's possible to stabilize all these things if you work hard enough. And so let's pretend that this system is stable and try to carry out this exercise of turning on. So again, you want to turn on a potential for the gauge field on the D8 brane. That's a chemical potential for these fermionic strings, and we'll make a density form. And so at weak coupling, at least, the effect would be that you would have a 2 + 1 dimensional gauge theory coupled to a density of fermions. In the brane picture, you've turned on this chemical potential. There's an electric field that runs from the boundary of the space along the D8 brane down to the horizon. And it's a nice result by Kuliksisi and Parnichev, which says that if you now look at fluctuations of the D8 brane around this, you look at the 2-point function, and it looks a little bit like you've got a Fermi surface, in the sense that there are states at omega goes to 0 with finite momentum. And if you think about that, That's not something we ever see in a relativistic system. In a relativistic system, of course, omega is always greater than or equal to k. But a Fermi liquid has this distinctive behavior that we can, here's our Fermi C, and we can take a fermion out from here and move it over here. And that has very little cost in energy because we've just moved it this far in the radial direction, but it's changed the momentum by a huge amount. And so there is some evidence that this picture knows about this picture, and so one is really building maybe a Fermi C. The problem is that these field lines, it's not obvious the way I've drawn it, are really scrunching together, and the field is getting very large near the horizon. And this calculation really isn't self-consistent because the field back reacts on the space-time geometry, and also the effective action you're using, the Dirac-Born-Infeld action for the brain, is breaking down. And I should say, some of the earlier things I mentioned today, you perturb a system, you find that some perturbation grows large at the horizon, and then, as in some of the other examples, it's not obvious. You have to spend some time figuring out how that resolves itself, what really happens there geometrically. And so far, nobody knows, in some sense, what the effect of the back reaction of this is on the metric, and whether this picture survives. But this is again, it's intriguing. It would be nice to understand better if this is really telling us something about Fermi liquids coupled to strong gauge fields. Yes.
So I have two questions. The
Yes.
first one is that how does the Higgs phase of this setup look like? So can we still interpret the D2 rings as some kind of instantons on the gauge?
No, I didn't call them. They're not instantons. All these dimensions. Sorry, these dimensions are all spatial, and everything's extended in time. They're not instantons. So.
Okay, no, when the D2 collapses on the D8, or is it like always?
But I mean, it's two objects. I mean, they're objects which are persistent in time. They're not instantons. So I'm not. It's.
The D2 rings, the D2 D6 case.
Yes.
In their D2, the Higgs phase has an interpretation in terms of instantons.
I'm not. When you mean the Higgs phase, you mean the coolant when we separate the D2s, or?
No, when we bring the D2s and the D8s together.
I wouldn't call that the Higgs phase. I would, because I mean, what's being Higgs? I mean, I would just call that the opposite. I call it the unbroken phase. We can talk after if you want. Yeah. Okay. So. In 60 seconds, I'll just describe the last item on my list, which is if we go back to the D equals 3 theory, the D equals 4 theory that we started with, and replace the n equals 4 gauge multiplet with n equals 2 gauge multiplet, which we can do by appropriate orbifolding, and then replace that contribution to the beta function with fundamentals. So we get to an n equals 2 theory with nf equals 2n sub c. And this has, like the n equals 4 theory, a coupling which is continuously adjustable from 0 to infinity. And so you would think that as you take the coupling to infinity, you are morally entitled to find some dual theory in which you can calculate, right? That's kind of the rule. If you find something that can be taken to infinity, you can find a better way to calculate. And what's interesting is that as far as anyone knows, and I think the only published really work on this is by Rastelli and collaborators, as you take the coupling to infinity, in the n equals 4 case, the ADS space gets large in string units. But in this case, it seems as though everything stays string scale, which means that although it's strongly coupled, the anomalous dimensions are only of order 1, And if there's a dual description, it's going to be stringy rather than supergravity-ish. And so so when I told you what the conditions were for the duality to hold, I said strong coupling, but strong coupling does not imply large anomalous dimensions. It really is, to get a supergravity, you need strong coupling and consequently large anomalous dimensions. So here's another open problem. How do you calculate in this theory at strong coupling? Maybe there's a good string dual, and that would be a nice thing to understand. Okay, so amazingly, I just about exactly got through my whole outline. I think I wore you all down. But by and large, you've been a great audience. I think I've been at 4 TASIs, and you have been the best audience, the most persistent and the most questions. So thank you. I'm here, by the way, all week to hear the other lecturers if there are more questions in real time. Yeah.
Just one comment about NF equals 2 MC.
Yes.
It's